Welcome, and in this video we are going to prove that indeed wave-like solutions are possible for the Maxwell equations. So since we are going to play with the Maxwell's equations, let's first write them down one by one. So the first Maxwell's equation we have is del dot D equals rho. The second one we have del dot B equals 0. For the third one we have del cross E equals minus partial B over partial T. Then for the fourth one we have del cross H equals J plus partial D over partial T, where J is the free current density. And in these four equations we have rho. In the first equation we have rho, that is the rho is the charge density, and D, here we have D, which is the electric displacement, and it is written as D equals epsilon naught epsilon r, and E, where E is the magnetic field, epsilon naught is the permittivity of free space, and epsilon r is the permittivity of the material, and here B is the magnetic field. And in the third equation again we have electric and magnetic fields, and in the fourth equation we have H, that is the magnetic quantity, and this magnetic quantity is given by H equals 1 over mu naught mu r, and B, where mu naught and mu r are the magnetic magnetic susceptibility, magnetic permittivity of free space and the medium respectively, and J, as I told you earlier, is the free current density. So we are going to prove that the wave-like solutions are possible for these equations, right? So let's assume that we are in a region where there is no free charge. Since there is no free charge, there is going to be no displacement current, so we can write rho equals 0 as well as J equals 0. And so the first and the third equations can be written as del dot D equals 0 and del cross H equals partial D over partial T. Now what we can do is put the value of D and H in these equations, and we are going to get is epsilon naught epsilon r del dot E equals 0, and here we are going to get is 1 over mu naught mu r del cross B equals epsilon naught epsilon r partial E over partial T. So there is a reason why I am doing these equations side by side. So here we have del dot E equating to 0, and we can also write it del dot E equals 0, right? Okay, so here we have this third equation, right? From this third equation, what we can do is we can take its curl, right? Now why we are taking its curl? Because we have here the magnetic field, and we need the curl of magnetic field, right? So let's take the curl of this third equation, and what we are going to get is curl of electric field equals minus curl of partial B over partial T. Now since these both are operators, this del and partial T, so we can interchange their positions, and we can write minus partial over partial T del cross B, right? And here on the other hand we have del cross E, and from our EMT knowledge or the algebra calculus we did there, we know that the curl of a curl equals divergence, sorry, not the divergence, it's the gradient of the divergence minus Laplacian of that vector, right? So what we can do here is we can write del that is the gradient of divergence of electric field minus Laplacian of electric field going to be equal to minus partial over partial t del cross B. Okay, so since del dot E equals 0, this term will be 0, minus sign cancels out with this minus sign, and we are left with del square E equals partial over partial t del cross B, right? So we can put this equation here, and what we are going to get is we are going to get del square E, that is the Laplacian of E, equals mu naught mu r epsilon naught epsilon r partial over partial t of partial E over partial t, and this is partial del square E equals mu naught mu r epsilon naught epsilon r partial square E over partial t square, right? So since we are in a medium where there is no free charge and there is no current, displacement current, so we are in a region with mu r and epsilon r equals to 1. So this equation reduces to del square E equals epsilon naught epsilon not epsilon naught epsilon r, it's epsilon naught mu naught partial square E over partial t square, and we know that the speed of light, it is given by c equals 1 over under root mu naught epsilon naught, right? So this becomes del square E equals 1 over c square partial square E over partial t square, right? And this is the equation of a wave moving with the velocity c, so moving with the speed of light. So I'm not going to derive the solution of these type of equations. You guys have probably done that in the course of ordinary differential equations, or maybe in oscillations course or the waves course. So this is pretty straightforward, that these type of equations give wave like solutions. So we have proved that the wave like solutions are indeed possible for the Maxwell's equations, and these solutions are indeed transverse solutions, that the propagation of wave will always be perpendicular to the changing electric and the magnetic field. We can do that as an exercise for maybe another video, but for today it's all that there are wave solutions possible for Maxwell's equation, and that's how we derive that. Thank you.